Well, I wish you'd told me, Bob.
Whatever.
Okay. Here we go.
Okay. All right. Well, for our first speaker of the semester, Roland Allen is going to tell us about modeling
Okay,
dark matter.
I'm assuming we have an audience here, people who may not be high energy experts. Okay, so I'll address this to a general audience. So this is the beginning slide. So here about, so I have basically I have to cut this down, way down. It's already like a 3-hour talk. So
you can go to the usual time. People are free to leave.
Okay.
If they have things to
Here we go. So very quickly, here are two of my heroes of dark matter, and there are 3 types of experiments that are planned, and I'm going to talk rapidly, but also I'm going to skip a lot of technical details. And in fact, I'll give the talk to anybody who wants to see the technical details, and the papers are there too, of course. So this really is the first time of the hundreds of talks I've given that I was late for a talk. It really is. Okay. So, I'm going to, first of all, try to persuade you that this is the dark matter scenario, okay? Now, this is a very bold statement, but what is great about this, this is a review of the abstract. And this time, for the abstract, as we go over it, I'm going to emphasize these points because this is the point of the talk.
Can you do me a favor and use the pointer, use the pointer and the clicker? Because this screen is way too bright.
It's too
This is
bright.
overkill. I'm blind.
Oh, that's an impressive pointer.
Well, should I stay with it?
Yes, it's like the military grade.
I have one that's more obnoxious, it's a violet pointer. Okay, that's the, that's so pathetic.
Well, I keep my eye vision.
Okay. Susie's complaining about this too. She's heard me give many talks and she's complaining about this. But so I have to do the pointer without at the same time advancing the slide. You know, you plan things so carefully and then everything falls apart. So there we go. So I'm going to dwell on this for about 3 minutes because it is the outline of why this is the perfect dark matter scenario. First of all supersymmetry is safe. Right now, supersymmetry is regarded as being in trouble by a lot of people. And I'll come back to the reasons very briefly in a moment. This saves supersymmetry. All the known well-known successes of supersymmetry are preserved with natural values for the parameters. But we have a multi-component scenario, so there's another dominant dark matter particle, and there may be others, but there's one more dominant dark matter particle which supplements the neutralino of supersymmetry. Let's see if I can do this correctly. There's a theorem that establishes this dominant component, according to this scenario, has a mass that's less than or equal to 125 GeV. I don't see Rupak here. I actually made a bold bet with Susie present when Rupak was there that the mass would be exactly 125 GeV, but that is not the theorem. The theorem is, that's a simple scenario. The theorem is the mass has to be less than 125 GeV, and this is actually the thing this theorem is correct. I mean, the fact this is the correct way of stating it. The Gates couplings of this particle are precisely defined, so one can make precise predictions about the phenomena where the Gates couplings are the relevant couplings. But there's also a Higgs-mediated coupling that's actually much more important for either direct detection or indirect detection. And this is consistent, by the way, with supersymmetry. For spin-independent interaction, the direct detection, for example, the Higgs mediation is the dominant mechanism that gives us the best chance of seeing things, seeing neutralino, as well as this particle. So let me skip over some of these things that we'll come back to that are there already in the abstract. Now we know that supersymmetry and dark matter WIMPs are regarded as being in trouble by many people nowadays. A lot of people say they're giving up on these things, but it's too soon to give up because we know that historically important discoveries take a long time. I actually went to a supersymmetry conference in the late 1990s and heard 2 speakers back to back say they were giving up on supersymmetry unless it was discovered in the next few years. We're now more than 20 years later, and more people are tending to give up. But there's no reason to give up yet. It takes a long time for these important discoveries to be made. And the Higgs black holes and gravitational waves are examples of this. Here's a relevant fact. It's difficult to be consistent with the observations in astronomy for the abundance of dark matter in different ways. If the neutralino, or dark matter, or a supersymmetric candidate, is the dominant component of the dark matter. And let me skip ahead now because there is limited time. This is a paper by Howie Bayer and Vernon Barger and Xerxes Tata and their graduate student, Asim Gupta. They pointed out that if one has a multi-component dark matter scenario with a supersymmetric neutralino as one of the components, like a wild stab, say 10%, and some other particle dominates, they were thinking in terms of axions, then the tension between the SUSY dark matter and the observed dark matter abundance is ameliorated. In our scenario, the additional dark matter particle is not the axion, but it results from an extended Higgs vector. It's extended in a different way from what you've seen in other talks. Here are our papers down here, which I also gave reference in the abstract. There are 4 theorems about this particle. I use theorems in quotation marks, but actually there are 3 rigorous theorems regarding this particle. The first is that its mass must be less than or equal to 125 GeV. The second is that the gauge couplings are precisely determined. The third is, and I'll show you the theorem in a moment, the rigorous theorem, indicates the coupling to the Higgs boson to this proposed particle is comparable to the coupling of the neutralino to the Higgs boson. And finally, another rigorous theorem is both this new particle and the neutralino will exist as stable dark matter candidates. They both have an R parity of -1, but they coexist. There may be other dark matter components. It's a multi-component scenario. Axions may be there, and of course there's an very active search for axion dark matter. But these other candidates, and if you go to the conferences, you hear all kinds of proposals for new candidates for dark matter. There are hundreds out there now, I'm sure. These speculative candidates have very poorly defined abundances and very poorly defined masses, whereas these candidates, the neutralino and this new particle, would have well-defined abundances because we have the Went miracle working in favor of both of them, and they also have relatively well-defined masses. In this case, a very well-defined mass by this inequality. So, we have both particles. I'll race through this. The new particles are an extended Higgs sector in the sense that the Higgs boson, all Higgs bosons, are regarded as amplitude modes that are analogous to the amplitude modes that have been seen in condensed matter physics for decades now. And here's a reference to one of the papers by Chandra Varma, who came here not long ago. We have given this name, it's published now as a name, Higgsons, to these particles. We use a capital H for them. We're aware of the fact that capital H is used for Higgs bosons by some people, but we use a capital H for them, small h for all Higgs bosons, and of course an H squiggle for the Higgs-Zenos of SUSY. I'm going to race through. First of all, we have the prospect of indirect detection. I'm doing this for those people who are not absolute expert, who are not experts in dark matter detection. So here's one possibility. Here it's showing the supersymmetric neutralinos, but this also applies to our particles. They can annihilate in space, and out comes other kinds of particles ultimately. This includes antiprotons, positrons, and gamma rays. And we'll come back to those in a moment, showing the experiments. Here's AMS, sitting on top of the International Space Station. Here's a slide from a talk that I heard this summer, a few weeks ago, in Ghent at the European Physical Society High Energy Conference. This indicates evidence from antiprotons for 100 GeV-ish dark matter. And this result from the antiprotons is observed by AMS, are consistent with one of the other prominent satellite experiments, that's the Fermi Light experiment, observing gamma rays from the galactic center. So here's the quotation. I didn't leave myself enough time to do justice to this, but these are intriguing results. Here's one paper published this year by this group. Here's analysis by a different group. It's the same data. These are antiprotons observed by the AMS. Here their estimate, the modeling gives about 46 to 94 GeV for the mass of the dark matter particle. Here 40 to 130 GeV roughly. And they both make the point that the signal is compatible with the dark matter interpretation of the galactic center gamma ray excess. Here's a quotation from another paper. This is a 2017 paper analyzing the Fermi light data. And here you'll see that they, in their analysis, they're projecting dark matter mass of 50 to 190 or 10 to 90 GeV, depending on the model for the interactions. So we have some evidence, possible evidence, that something is going on with respect to the, for indirect detection of dark matter annihilation in space. But of course, the big thing always is there are astrophysical sources that serve as background. But there is some evidence, tentative evidence. Let's come to positrons. That's our third example. In this case, the positron excess does not indicate particles that are down around or less than 100 GeV in mass, but the dark matter particle would have to be up at about 800 GeV. That's okay in our picture. We would love this because this would be our neutralino. The neutralino, which also is there in the same scenario, being observed at this higher mass, and we expect the supersymmetric particles to be at higher masses than the 125 GeV limit for our particle. That was indirect detection. How about collider detection? Here's our collider. Here's the LHC. Oops.
One thing.
Yes.
AMS, any AMS exploration is very tightly constrained.
Which is?
Very tightly constrained by Planck post-recombination cosmic particle background.
The Planck observations constrain the abundance.
No, there is another thing. Planck also constrains the post-recombination, that means dark matter annihilates into photons. Those photons come and then affect your cosmic microwave background
You're
sky.
talking about the cross-section for annihilation.
Yeah, so cross-section means they kind of mostly rule out AMS, any excess.
Let me see the paper on this. What paper is that?
Oh, this is kind of 2 years or 3 years back.
Let me see the paper, Bhaskar.
Yeah.
I would like to.
So let
I'm
me
here
show you.
I'm here to learn too, for sure. But these papers that are being published in 2018
Yeah, no.
in PhysRevD.
Also, actually now AMS only survives on some decaying dark matter model.
Yeah.
Because that's the problem.
Yeah, I agree with these observations. Okay, these are not the most critical for us. This is the higher energy observations, right? And of course we have the Hess observations and all the others too. Yeah, I know what you mean. So AMS is. Are we talking here?
No, I'm
so
just
AMS.
showing you the.
Well, you're finding the paper. Fantastic. So I need to see this paper. AMS is certainly in some kind of trouble with respect to its status for years to come. Certainly.
CMB sky.
Say again?
Post-recombination CMB sky.
Yes, but we're talking about these observations of the positrons.
Exactly.
Okay,
So
not the
means
antiprotons or
not
the
the
gametes.
antiprotons.
Yeah, okay.
Anything annihilates into
Okay.
electron, positron,
Okay.
they would affect the cosmic microwave background sky because it's made
Yes.
out of photon. Electron, positron, a radiate photon, that would affect. So that's the
Okay.
way.
I'll look at
And-
the paper. If
yeah.
I'm understanding this correctly, though, what this does is it puts our supersymmetric candidate in trouble, but our candidate is still in good shape. So I'll live with that.
Any candidate would be in trouble, not only supersymmetric.
We'll talk about this,
Anything
right?
which explains AMS will be in
Right.
trouble.
Okay, so then let me go to the collider detection thing. And I have a question here which I really want to iron out with our experts here, the CMS experts, and that is disappointed not to see experimentalists here. And my big question here, and I have to race through all this, is the invisible Higgs decays that would indicate our particles or neutralinos being seen. Limits have been placed, like a 20% limit on the branching ratio. And my big question is, this is for particles that have masses of less than 60 GeV. So the limits there are there for those particles. This is for a real Higgs boson. A real Higgs boson can only decay into a pair of particles that have masses that are roughly less than or equal to 60 GeV because the Higgs has a mass of 125 GeV. But a real Higgs boson can't decay because if you go to the frame of the real Higgs boson, in that frame the Higgs boson's at rest, and so the particles that are emitted in that frame have to have masses that are less than or equal to 60 GeV. But if you go to a virtual Higgs boson, it's a different story. And so I'd like to really understand, and I put this in big letters, can we possibly think in terms of analyses that are for virtual Higgs bosons where we can reach higher above the 60 GeV limit for the invisible Higgs decays that have been seen so far. So maybe I should ask Truki and the other CMS experts about that. I actually emailed some Atlas people, and I didn't get a response yet, so I'll talk to my people. Then we finally come to direct detection, and in direct detection, of course, we're looking for recoil off a xenon nucleus or a germanium nucleus or something like that. This is a pessimistic slide, not very funny to those who are looking for dark matter, but so far the story has been, if the reporter asks, have you actually detected dark matter, the answer is we're getting extremely good at not detecting it. The backgrounds are now way down, and there is pride in the experiments being so good, and the mass is being increased to the point where where there's very good reason to believe that detection is finally getting near. Certainly much better reason to believe than there was in the 1980s, 1990s, and so on. So direct detection, LZ is perfect. We have an LZ presence here. I understand that Bob Webb is still working on LZ, right? We have this xenon experiment, which is equally good, at least equally good. And finally, we have the possibility that these particles that we're proposing might have lower masses, maybe down to 2 GeV, who knows? A superseding EMS might be able to see these particles too if they have lower masses than the upper limit that's shown here. And of course, we have a very strong superseding EMS presence here with Rippak and Dave Tobach and others. So I'll skip over these diagrams. This is a diagram that won't work because this is gauge interactions. This is even worse. This is second order gauge interactions. Our particle has very weak gauge interactions for either direct or indirect detection because the dark matter particles are slowly moving. And there's a momentum-dependent interaction here. But the Higgs mediation is very strong. This is the favorite mechanism, as I understand it, and Bosco can hopefully verify this. These are probably the diagrams, the favorite processes for direct detection of neutralinos, and they're also the favorite possibility for our new particle. Namely, our new particle is moving along, and it's a Higgs, there's a quark in the nucleus. The coupling of the Higgs to a quark is proportional to the mass of the quark, and up and down quarks have small masses, so there's a small coupling here. On the other hand, if the mass is too large, the top quark, bottom quark, charm quark, then the abundance in the nucleus is very small, and the optimum scene thinks this would be a strange quark, which has a somewhat higher mass and is there in some abundance inside a proton that's colliding at the LHC. So that's one diagram that's possible. Then we can go straight to the extremely massive top quark. So we can have a virtual top quark triangle and couple, our particle couples to the Higgs, it then couples to the top quark very strongly. The top quark then couples to the gluons that are in the nucleus. So this is the favorite way of observing for direct detection, and our particle should be just as strong, roughly as strong, for this kind of process as the neutralino. And this is a reminder, only for those people who have never seen things before, what the neutralino is. The neutralino, of course, is a linear combination of the 4 neutral superpartners, the photino, the xeno, and the 2 Higgs xenos that have to be there in supersymmetry. This is very technical and certainly don't have time for it. The only thing that I want to mention here is that there's a real correspondence between even the software that's used for neutralinos and what could be used to do the same processes for our particle. Very similar. And in fact, here's a correspondence. If this is the coupling strength of the neutralino to the Higgs, and this is the mass of the neutralino, then our particle should couple in the same way as a particle, as the neutralino that had this product of 60 GeV. So we have this correspondence between how our particle can be seen and the calculus that can be done with software, and the same for the neutralino. So one of the other things I want to investigate is, can we get into the software that's used for neutralinos and use that for our particle? So here's some other diagrams for indirect detection and collider detection. I'll skip over this because I want to end at 50 after, which is only about 9 or 10 minutes away. One of the big things is here, supersymmetry has given us a tremendous plethora of particles, new particles to look for at higher energy. So if supersymmetry is seen, then this enormous range of this new world, new physics associated with supersymmetry will open up. But here we're doubling the range of possible new physics. We now have the extended Higgs sector that we're proposing, and we also have SUSY. Together, they will give us an enormous number of new particles to be seen experimentally in the near future, at least the foreseeable future. Now, what is our particle? Okay, I haven't said what our particle is, basically. We have three types of particles in the standard model. We have spin 1/2 fermions. The first of these is the electron observed by Thomson. It is very unlikely that Thomson envisioned the electron as being a 4-component Dirac field when he discovered it. To him, it was a little charged particle. It was not a 4-component Dirac field. Surprises were to lay in the future. When Einstein proposed the photon, he certainly didn't envision the richness of quantum electrodynamics in the standard model and so on. So enormous richness came after the discovery. Now we have a new discovery. Here we have the discovery of the Higgs in 2012. And who knows what richness may be associated with the Higgs. So in our model, or in our theory actually, the Higgs is an amplitude mode for an extended sector. Now, there's an unfamiliar feature here, and that is there is a very mild breaking of Lorentz invariance. Our particles, first of all, for every other type of particle, for all the particles in the standard model, we have exact gauge symmetry and exact Lorentz invariance. So only this new sector that should be observable at very high energies, maybe up to 250 GeV, only this in this new sector will there be this mild violation of Lorentz invariance. Let's remember, though, that these old invariances, P, CP, T violation, have been found to be violated after they were originally regarded as being sacred principles. In 2012, finally, Babar showed direct violation of time reversal invariance. So these invariances have been shown to be broken as one got to higher and higher sectors. Here we have a new sector at very high energy, and the proposal is there is this very mild violation of Lorentz invariance. But our particles, even our new particles in this sector, still satisfy a lot of things. They still have exact rotational invariance. They still have exact gauge invariance. There's Lorentz symmetry except for these new particles, the Higgs-on fields and the Higgs-on particles. But even these particles have a relativistic equation of motion, and they satisfy E equals mc squared and all the normal things that we associate with classical Einstein relativity. So it's a very mild violation of Lorentz invariance. But as soon as you break Lorentz invariance, you no longer really have the spin statistics theorem, which is a very sophisticated theorem that assumes complete Lorentz invariance under boost and everything else. And you need this Lorentz invariance. There have been many attempts by people. And this is one famous person. I told that Michael Berry tried to give an argument for the spin statistics theorem for non-relativistic systems, but we showed in the paper a long time ago in PhysRev A that there is no spin statistics connection in non-relativistic quantum mechanics. You need invariance under a boost, and we are missing that invariance under a boost for this one sector. And as soon as you break this Lorentz invariance at all, you are breaking the spin statistics theorem. So now we have these spin 1/2 bosons. So our particles, we could have invented a contrived model where we have amplitude modes of fermions. But no, what comes out of the theory is not amplitude modes of fermions. What comes out of the theory, inevitably, is amplitude modes for spin 1/2 bosons. So the comment is, if you are frightened of spin-1/2 bosons, and this present scenario is terrifying, but the history of physics is a history of terrifying new ideas, okay? We can begin with the Earth moving around the sun, and we can go to all the relativity and the trend paradox and everything. So the point is we have to agree with experimental observation, and we have to be mathematically consistent, but we don't have to agree with our prejudices or what we've seen in lower energies in different sectors. So these are spin-1/2 bosons, and they're put together to form the amplitude modes. So here is a multi-component object. Here's an amplitude multiplying a constant spinner. And as long as you don't see the internal degrees of freedom of this multi-component object, then we get back to ordinary physics. So for example, this complicated looking Lagrangian reduces to the simple Lagrangian that has a very familiar look. These are the amplitude modes. This is the kinetic part of the Lagrangian for a Higgs boson, for one of our amplitude modes. So we get back to standard physics. If you don't excite these internal spin-1/2 degrees of freedom, all of standard physics is regained where it's been observed. Now, these are very technical slides. I'm going to skip over them. This is how supersymmetry fits into the picture. This is why this has to do with Lorentzian invariance and bosons and so on. So I'm going to quickly say that where our theorems come from, the mass of the Higgs boson is this. And with the Higgs boson is regarded as being an amplitude mode that spans these Higgsons, these spin-1/2 fields. So in a sense, it's composed of these spin-1/2 fields. And there's a theorem. So these are rigorous theorems that the square of the mass of the Higgs boson is equal to an average over the mass squared for all these Higgson modes that go into the Higgs boson. Well, if you imagine a group of people, if you have a group of people of varying heights, you can certainly say that the shortest person has a height that's less than or equal to the average height of the group. And so the mass of our projected particle has to be less than or equal to the mass of the Higgs boson, which is now measured to be 125 GeV. Here's a similar theorem with respect to interaction strength. This is the standard, B over 2 is the standard coupling parameter for the Higgs boson. It has a value. Now that we have the Higgs boson, we know what this value is. It's roughly 1/8. This is the standard self-coupling or quartic coupling constant for the Higgs model. And this relates again the average value for the couplings of our particles to the Higgs boson. So I'll make an analogy again. If you have a number of people that have different weights, and the average weight of this group of people turns out to be 100 pounds, it'd be quite unnatural for a randomly chosen member of the group to have a mass of less than 10 pounds. Okay? So naturalists would imply that the coupling strength for our Higgson should be comparable to the coupling strength, the self-coupling for the Higgs boson. So these are rigorous theorems. And then we have another rigorous theorem that is that both the neutralino and the Higgson are stable. Why are they stable? Let me skip over some technical details again here. The reason that this works out is that the neutralino is a fermion, and our Higgson is a boson. And then you can go through the argument that's given here. It's given in our papers, and it's given here on this previous slide down here. It has to do with the fact that the mass dimension for a fermion is 3 halves, the mass dimension for a boson is 1. And so you can immediately conclude through this little simple argument that the Higgson and the lowest mass Higgson and the lowest mass neutralino have to both be stable. So we have what automatically emerges from this picture is a multi-component picture for dark matter. And let me just skip over some of these other things here. Let's just say we do have the Wimp miracle. I'm seeing this 10 after, so I'll very quickly. So we have the Wimp miracle. The gauge interactions are relevant here. The problems that supersymmetric candidates had, that the neutralino has, doesn't seem to be there because the couplings are different. And so, finally, these particles do have, like the neutrino, they have an arc area of -1. We have a limit on the mass. We have precisely defined reconnection couplings. We have a coupling to Higgs that should be comparable to that for the neutrino. And so supersymmetry has to come out as well from the same theory. And so therefore, we might have other components, including axions. And so the real thing is that the predictions here, they're experimentally accessible in the very near future. If this picture is correct, we have, as we said, a doubly rich plethora of particles and new physics to be discovered in the very near future. So thank you for your attention, and my apologies for being late.
Any questions for Roland?
So, Roland,
Yes. That's the paper, okay? And this,
the brown paper, and you can see it's ruled out.
yeah, what you ruled out?
The all AMS Pamela explanations, whatever theory you come up with, they are
That's
ruled
it.
out by CMB.
Well, you were not the referee for those two analyses, those two independent analyses that
we didn't
proposed this
publish
year in
those
Phys Rev.
papers, but this is the ruled out.
I'll look at this. I think there are details that were not really.
No, you say it's been out there. We have been writing papers on these things for
Yeah, I'm
the
sure
last
you have,
couple of
right.
years.
Yeah.
Just avoiding the CMB constraint is a serious
Okay.
constraint.
So this is a well-known fact, right?
Oh, yeah, very well
Okay,
known.
then how did those two papers get into Phys Rev D?
Which
Why are they
papers-
giving, why are they giving
which
plenary
one
talks
did
at
you publish in
conferences?
Phys Rev D? Which one you published? in
You
Phys Rev D?
overestimate the power of peer review with PRD.
So, but,
Well, let me look at this. This is the kind of thing I'm looking for. Thanks, Bhaskar.
But
Thank you
what
very
does this
much.
say? Does this say the experiment is wrong?
no,
Is there a
the
problem
AMS,
with
yeah,
data?
problem, so AMS observation is not necessarily due to dark matter. See, this experiment is showing that it could be due to pulsar.
Let me point
There is
something.
this Geminga pulsar which is also producing E plus E minus, probably is because of that. That's true.
I think the devil's in the details here, Bhaskar. And let me point out something else, that the Planck data also rule out the observations of, I think, for example, Lucas Macri and Adam Rees and so on, for the Hubble constant, because there's a, these things
No,
are.
there could be a cosmology there, so they don't
Yes.
rule out anything. They are measuring H naught at a different time.
Yes.
And Lucas is measuring H naught
Yes.
at a present time. So there could be
Yeah,
cosmology
it would be
which
new
can
physics,
connect
and that'd
this.
be nice, right?
Right.
I want to look at
But
this
this is
paper.
kind of at the same time.
Yes. Yeah, but before we say we throw away all this, I want to look at this because I
Only
think that-
way you can explain AMS,
Yes.
but dodging this, is decaying dark matter. That means dark matter decays. All of a sudden now, it was not decaying at the CMB recombination time, which
Let me-
was Z
Right.
equals to 600.
Yeah, can you give me a precise version of what we're talking about annihilation cross sections? Because this indirect detection.
Annihilation into electron-positron, which explains AMS.
Right. So you're saying they're placed limits on the
Right,
cross section.
right,
Wait,
right.
hold on, let me say it
Right.
clearly, okay?
Yeah.
So we have a well-defined
Right.
target, okay? Let me give you a well-defined target.
Right.
So you're saying that, we're talking about indirect detection as measured by AMS or Fermi, okay?
Right.
And you're saying that the cross section for annihilation producing these
Positron
products,
excess.
that the cross section has,
Right.
the limit has been placed,
Right.
that it has to be lower than, it's an upper limit.
Not low. So AMS needs about 10 to the power minus 24
Uh-huh. For the annihilation cross
centimeter
section.
cube per second.
But is the limit a lower limit or an upper limit?
So this is, that means it's ruled out from 10 to the power minus 25.
But
So
but
that
the,
means
the,
this
the,
is
the
giving
Planck
a,
data, but the Planck
Planck
data,
data is giving a lower limit, which is
Lower.
covering your.
a lower limit to the cross section for annihilation.
Right.
Okay,
It has
and
to be
this
lower
also
than that.
has implications for modeling the production of dark matter.
Right.
It spills over to that area. Okay, let me look at this. I'm not convinced because I think the devil is in the details. But
This
thank
one?
you, Bhaskar. I'm very, this is
This
the kind
one
of thing I'm
devil
trying to
in
learn.
details.
Say again?
This one is the devil in the details. There is no detail. He said, if you explain Pamela or AMS by E plus E minus positron excess, then it's ruled out by CMB for the electron positron. Nothing else. There is no other thing. One-to-one correspondence.
Okay. Let me talk to you, and I'm very appreciative. Thank you very much. I really am very, I'm indebted to you for pointing this out.
Any other questions? Okay, Dr. Stein, take one.